very happy to have Professor Gregory Dudek from McGill's computers. I can't list all the places you are. Computer Science Department. You're also at Samsung, and you're also at Mila and countless other places. Greg is a roboticist. Putting it mildly, he's a roboticist. He's a cognitive scientist with wide interests. And I think that you're going to find his talk today on building robotic intelligence that learns and accounts for human users very interesting and informative. Greg, I wanted to ask you, do you want to take questions during, after, or transmitted, mediated by me from the chat, or a mixture of those?
Oh, I'd love them during.
Okay.
But I will not look at the chat while I'm speaking for obvious reasons.
So I'll be monitoring the chat and I'll let you know if there's something worthy of your attention.
Yeah, that would be great. And it's worth noting for the audience, as you already know, that the talk is a bit of a hodgepodge. It's got a number of different things combined, partly because, well, for many reasons. I usually tell my students to keep this talk narrowly focused, but I'm not very good at doing that myself because there's a number of threads I want to weave together here.
Okay, one other thing you might want to keep in mind, which is that it's a mixed language audience. And so things like RL have to be defined because they don't know that you're talking about reinforcement learning.
Okay.
No, just the acronym has to be, and things like that.
I understand that. And j'ai l'habitude de parler un petit peu en français, mais pas tellement facilement. Je manque le vocabulaire tout le temps, mais si vous voulez poser une question en français, probablement je peux répondre, mais en anglais.
C'est beau. D'accord. Alors, les questions peuvent se poser en français ou en anglais. And if I understand correctly, if it's put in the chat and it's interesting, you'll let me interrupt you. Go ahead.
Absolutely. Interrupt away. Yeah. I just realized I should have a clock, doubly so in that case. Too bad.
It's all right. It's all right.
Yeah. Okay. Okay. So I'm going to talk a little bit about robotic intelligence, robots that learn, robots that take human users into account. What you're seeing right now is a boat that we deploy in the Caribbean to do data collection, which is a very interesting sub-problem in itself, and one I'm not going to talk about, but it makes nice eye candy for the background of the video. I do a lot of work in marine robotics, though, and I will talk about that a little bit, both through some examples, and I'll actually motivate that problem because I think it's got an interesting appeal to all of us about being an important problem that we should work on. So let me say the obvious thing, that all my work is really due to my students and my collaborators. Many of my collaborators are my former students. Some of the names are listed here. Travis Manderson, Sandeep Majana, Dave Meager, Yanis Raklaitis, Florian Shkurti. Let me talk a little bit about what I mean by robotics, or what I think about when I refer to the robotics. And so robotics is really the creation, we can think of it as the creation of machines that combine sensing and action in some typically biologically inspired way. But I think that's a much too narrow definition of robotics. And so we might say, well, robotics is the creation of machines that combine intelligence and sensing and action. No, we have intelligence in there. And so sometimes I like to say that AI, or machine learning, is a sub-area of robotics, which is something I do feel. It's not a complete containment relationship. It's like physics and mathematics. Physics and mathematics are deeply, deeply interwoven, but they're not quite the same thing. But you can't have physics without math. And arguably, you might not have math if we didn't have physics. That's a harder claim to make. I think another thing we might define robotics as even more ambitious goal is the replication of biological systems. Let's assume that says of. So basically doing what biology does with machines, I think that's still too narrow. I think we'd like to say we'd like to replicate human performance. So whatever people can do, we want to learn how to do eventually, maybe not this year. And then even more ambitious, I think we want to create superhuman systems. And that's clearly where we're going now. And we've seen examples in both robotics and machine learning of machines that use learning to do things better than humans can do them. And so I think really, I'd say the big aspiration of robotics sounds a little grandiose, but it's the creation of super biological life. That is the creation of agents in the world that can move around and replicate all aspects of biological performance, eventually including reproduction, but actually do them in ways that are better in some sense than what biology can do. So of course, it's not just the creation, it's the understanding along the way. Although in the world of machine learning, understanding becomes a very, very slippery term to use. So that's kind of my notion of what this field is about. ridiculously ambitious. Of course, any one of us can only do a little tiny piece of it. So, the notion of robotics has been around for a long time. And I think the naive view of it is it's systems that contain a planning component, an action-taking component, and an observation. And those are linked together through the real world. And this is a kind of model of robotics that developed probably in the early 1970s, a long time ago. And I was talking to Stephen at the beginning before the talk about David Marr and his role in formulating some of these very idealized views of how robotics, perception, the mind works. I think this is fundamentally not accurate. We can think of often the planning part, we think, oh, that's the brain, and observing is the eye, and action is our hands and our feet, and that moves around our robot. But that's really just an incredible, it's such a bad oversimplification that I think it's fair to say it's really wrong. Although I actually use this slide in undergraduate teaching sometimes, but sometimes I say it's wrong. I think the more correct kind of diagram would look something like this, much less pretty, but we have perception, we have feedback through the world, we have action, we have awareness, all kind of overlapped and interleaved. And underneath all of this, underneath awareness, we have some notion of an internal simulation of what the world is doing and how our effects will impinge upon the world. That's part of both awareness, but also preconscious behavior. And so there's a whole chunk of non-mindful cognition all the way from the cerebellum upwards that also is part of this. And so in the end, I think it's fair to say that robotic systems and also cognitive systems end up having a very complicated interconnected structure. And I think there's a beautiful kind of demo of some of this here that I'll show. Yeah, I got my slide out of order. Yeah, I'll talk a little bit about, so I'm going to talk a bit about learning for versatile platforms, about human-guided activity, so using humans to teach robots, and about robustness in harsh environments. Here's my video. So this video looks like it was taken in the 1970s. It's from 2005, and it's a video about tactile performance, and we're going to see a person lighting a match. And so the problem here is the person's tactile feedback from their fingers has been reduced by anesthetizing their fingers with dental anesthetic. And you'll see how hard it is for them to light this match. And so the take-home message here is really that their ability to plan and sense in multiple ways, right, both visually and with tactile sensing, are deeply intertwined. And so as soon as they lose good tactile feedback in their fingertips, just lighting this match becomes super important. So I use this to motivate some work we're doing on tactile sensing, which is not in this talk. It's part of my role in some other organization. But it's kind of a beautiful illustration of also the complexity of making inferences and doing planning and sensing.
Okay, there was a question there about why you separate feedback from perception, or do you?
I think, like the fully realized version of that figure would have everything interwoven in an impossible way. But that doesn't make much of a figure anymore. And so I think, like historically, I used to be a computer vision guy. So if we think of what vision, there's still an element where we take the sensor and we interpret the sensor measurements. And that's probably inextricably linked to some of the sensors. And then from those measurements, then we still have to do some sort of feedback process where we close the loop and see how they interact and how things change. And in the tactile case, that linkage is much tighter. But that's basically why. Does that sort of answer the question?
Thanks. Mel will indicate if she's satisfied. I'm satisfied.
Okay. So yeah, I guess I'll be more concise in my answer for the next question. So I think it's fair to say that perception, AI, machine learning, those are the core tools that allow robots to understand the world today, let them move around. And I think we need to be building and deploying robots that can help measure and map the natural environment. That's one of the constructive things that we do in our lab, constructive in the sense that we try to develop robots that do this, both understanding how they work as machines and how, what the nature of that intelligent reasoning process is that they might deploy, but we also want to actually solve real world problems with this. And I'll talk briefly about that. So I think, reiterating what I said earlier, I think it's fair to say that robotics can be seen sometimes as the technological embodiment of AI and cognitive science. It's taking these things and connecting them to the world outside. And I think the notion of doing the right thing, solving an AI problem, a cognitive problem, is typically ill-posed without considering what humans want, the human wants and the human needs of the people using these robots. And I mean ill-posed is a formal term, and it basically refers to problems where the solution is not well defined. Either it's ambiguous or unstable or somehow problematic. And I think in general, technological problems that we're trying to solve with robotics today need human input, not only to tell us what the right answer is, but on an ongoing basis to help derive those answers as we reason. So some of the kind of applications that we work on in the robotics world, and many of them in my lab, are things like environmental sensing. You know, how do we collect data over some cyanobacteria bloom, for example, to try to capture it efficiently? Or how do we do inspection on the ground for things? Or how do we track species? Or how do we do search and rescue looking for a person? All of these problems, you can kind of encapsulate them as, oh, I've got some data and I want to go and find the place where that data is most interesting. But in fact, doing that often involves many layers of actuation and feedback and this complexity of interaction. So this oversimplified view, I think, can be misleading. Even for these very simple applications, human guidance, in fact, turns out to be a really important aspect of the problem. Even to, say, map cyanobacteria, blue-green algae in our lakes. What part of the lakes matter the most, and what kind of blooms are most important, and where we care about data turns out to be a really important driver in actually making systems that don't just work sort of in the lab and in the classroom, but actually are useful enough to be deployed in the real world. So learning from people is a really core part of, I think, robotic cognitive development, or in fact, the exploitation of robotics technology. Even fruit flies use social cues from other fruit flies. And so it's clear that being able to take input from the outside world and from people is a really, really important part of our discipline. And I think it's one that in the robotics world is often overlooked. There's a whole field, I'll mention it later, I'm going to say something redundant now. There's a whole field on human-robot interaction. And I think it largely focuses on human needs and wants and almost psychological kind of phenomena. And it tends to be often disparaged by hardcore roboticists because it's like, oh, we're just trying to build an algorithm. And I think the realization that our field is coming to is that connecting to the people that run the robots is non-trivial and incredibly important, and needs to be, I believe, needs to be much more valued. So I'll talk about a few simple examples of that. I think it's fair to say that even in these exploration problems, we still need robots that are smaller and easier to deploy, more agile. We can plan and navigate in the natural world. We can choose what to measure. We need things that are fully autonomous and perhaps intelligent, whatever that means. So I think small and easily to deploy, we have some systems like that. I'll show you one that I think is kind of pretty. I think agility is kind of under control. I'd argue that planning and navigation is a solved problem. I think many people would say that with some important proviso. I'd say choosing how to navigate in nature is in fact not so well understood, because nature includes all sorts of exogenous forces. In the ocean, there are currents and there's seaweed and there's coral. On land, there's traffic and other people driving. I think, as you probably know, self-driving cars are confronted by tremendous problems as a result of the social interactions induced by other drivers. And so these kinds of interactions are super important. Choosing what to measure and when to measure it and how to value one measurement over another is actually a really hard problem that isn't well understood. And I think full autonomy is still an elusive goal. So many of these things, just for exploration problems, just to get the data that you might want to feed into a climate model or a biological model of the reef or something, that's still quite hard. And so just in data collection, I think there's a bunch of problems we can think of that include choosing where to go with some sort of observables, choosing what waypoints to visit and what routes to select, how to define novelty and what does it mean to find important data, what data is useful, and how do we value data? And then how do we categorize the data that we're getting to know whether it's good or bad, or how to form those underlying classes? So even in this kind of very simplified problem of data collection, there are a lot of complicated subtleties. So from this kind of very broad story, I'm going to move on to some concrete examples where we're actually doing some things. I'll look a bit at moving robustly, at recognizing and avoiding hazards in the world, at selecting routes and recovering from problems. So some of the motivating questions for the rest of the talk are, how do we enable robots to autonomously navigate so that they can explore or search for or find content that we're interested in? It could be cyanobacteria, or it could be, movies on the internet, but I'm not going to talk about the internet movies case here. How do we allow robots to interact profitably and acceptably with humans that control them? And I'm going to look at some very simplified paradigms for that interaction. And then how do we enable expert users, such as scientists, to specify what kind of data they need with only a few demonstrations? And so I'm going to address these problems by looking at them in a very concrete set of examples, as opposed to some sort of general case. So the first one boils down to what do we want from a data collection robot? The second is how do we expect them to behave around us, around human beings? And the third is how can a robot learn from examples? For example, if a scientist says, this is the kind of stuff I want, how do we find more of that? And how do we exemplify that data? Because typically if you say, I want to find an interesting rock on Mars, and you show a robot an interesting rock, it doesn't mean it should only be looking for that exact rock, which is the oversimplified paradigm that we'd be left with. And so from the robot's point of view, if we can anthropomorphize a bit, the question, or from the robot designer at least, the question is, how do we move? How should we execute our navigation? Where should we go? How do humans expect me to behave? How can I learn from their expectations on how to behave? And how can I extract data from examples to do the right thing? And so I think the simplest paradigms for robot learning from people are, imagine following the leader. We're going to have a person who teaches us what to do. And in the coral reef scenario, where we collect data on the reef, we've worked a lot on robots that can follow a biologist and collect data at the behest of a human leader that shows them. And so that seems like a trivial problem, just following somebody, convoying as it's sometimes called. But that's trivial only in kind of toy environments where perception is unambiguous and uninterrupted, and you can see the person you're following all the time. And that's not how people follow one another, as I'm sure you know, right? When we follow somebody, we don't do it by focusing on the back of their head continuously and on an uninterrupted way. And then learning from perceptual teaching, how do we consider conflicting cues and constraints? If we're going to learn from somebody, for example, we're going to do this navigation task, collecting data while we swim, we still have to take care of swimming and avoiding obstacles and taking care of exogenous inputs, something that makes us move, things like that. And so we have to consider how to trade off the need to move efficiently and safely and still learn whatever it is we're trying to learn. And then in terms of learning socially acceptable behavior, for examples, I think the question is, what are the cues and what are the rewards? And how do we even formalize the notion of social acceptability in the case of a robot? Like, what does it mean to move in a good kind of way? So a lot of the work that we do in our lab, and I think in our field as a whole, is based on reinforcement learning today. It's becoming a super important paradigm. I'm sure many of you know about it, so I apologize if this is a bit redundant. The nature of reinforcement learning is that we have an RL agent, a robot at the bottom, a reinforcement learning agent, think of that as robot. We have the world. The world is represented through a set of states, and you can think of those in the simplified case as just discrete states. So configurations of the world. We get some reward in each state, how good this is at this immediate moment. And we can take some set of actions, and those actions change the state or our state with respect to the underlying environment. And what we'd like to do is accumulate reward over time. And so you can imagine the game of Go or the game of chess, where the state is the configuration of the chessboard, and winning or losing is our reward, and moving is our action, moving our pieces. And this exemplifies an interesting issue, which is that in Go or in chess, winning or losing is computed at the end of the game. And so for all the moves in between the beginning and the end, you don't actually have an instantaneous notion of reward. We can formulate one in our heads like, oh, this is a good position. But that formulation is a construct in our minds. It's not an observation directly from the world. And so doing the so-called credit assignment, deciding how intermediate states benefit with respect to getting some long-term goal, that's kind of the key issue that reinforcement learning tries to address. Another example might be a robot vacuum. I have location and dust that I'm sucking up. I have residual dust, which I have to, so state is location and dust map. Reward is the residual dust that I'm picking up right now. And driving is the action I can take. And I'll note that the robot vacuum cleaner does not actually fit formally in the reinforcement learning paradigm, because in RL, we assume that the state representation is constant over time. But in fact, the world changes when you're vacuuming, hopefully. And so that change in the underlying world means it actually breaks many of the rules in the formal reinforcement learning problem. So I'm not going to go through all of the details of how to define an RL problem formally. It's based on the notion of a Markov decision problem. I'll just sort of mention the key terms: the state space, the action space, the set of transitions that take us from one state to another, some reward that depends on the state and action at any given time, a policy that lets us change our state over time. That's what we're trying to learn. We're trying to learn in a given state what action we should take to get us to the next state, and a discount factor, a factor that lets us trade off the future benefits that we might accrue versus what we're getting now. So if I'm investing in the stock market, maybe I don't care if my money is going to come to me in 20 years, I need it today. And so that trade-off is captured by the discount factor. The key middle thing I want to mention is this middle term, the scalar reward function. That's basically the goodness of the current state and action. And that's where the human plays a super important role in terms of defining what it is we care about in the world. So there are two kinds of, or the two big algorithm families for reinforcement learning with a bit of blurriness between them: model-free reinforcement learning, where the reward and dynamics of the system, the way the actions affect a state, are not well known, and model-based, where the reward and dynamics are learned. Typically, they're learned as part of the process. And so we want to learn those and then exploit them. And our policy, the behaviors we take, are determined by some set of numbers or parameters that are typically referred to as theta. And I won't go into those details. The model-based methods are very useful for things like driving, robotics, games, in terms of efficient learning, because we have much stronger notions of how our actions affect the world. The downside of that is we use a model of the effect of our actions on the world, but it means we're sensitive to the imperfections in that model. The big problem in RL in general is credit assignment, how to figure out how our current actions will affect benefits that come later on downstream. And that's kind of the name of the game. So inverse reinforcement learning is worth noting as well. That's a problem where we don't know the rewards. We have examples and we want to figure out the rewards that must have led to these examples coming out the way they did. And then we want to solve the RL problem to get a policy. Oh, and we need some data to get this done with. And this is very important for things like learning social policies, which I'll talk about later. We don't know how robots want us to move in their proximity. Imagine a cocktail robot that's serving cocktails at a bar, for example. How close should it come to people? Should it be allowed to bump into you? Is it okay for it to come close to you in the front versus the back? Those rules of those social norms are not exemplified or well stated in our minds or anywhere else. And many people have tried to build rules. It's really hard. And so this is a case where we have examples and we can infer the rewards from the examples. Yeah, Stephen.
Greg, what's the difference between inverse reinforcement learning and the credit blame assignment problem?
So credit assignment assumes that we know the states, the rewards, the actions. The rewards are the immediate benefits now, and we want to know how to maximize the sum of rewards over time. So for example, in the game of chess, we don't get any reward feedback as we play until the end when we either win or lose. And so we need to figure out what sequence of steps to take to get us to that good outcome at the end. And that's credit assignment. The fact that I, did some really dumb thing at the beginning and lost the game 40 moves later, that's a credit assignment problem. How to assign the blame for that bad action early on, right? It's easy to imagine that in the engineering context, right? Some engineer put a screwdriver, or a doctor left a scalpel in my stomach and I died 4 months later. The fact that it was that doctor leaving the thing inside me during surgery, assigning that blame to him early on, that's credit assignment.
Right. So
the problem of figuring out what really matters in the first place, the fact that I shouldn't bump people, or I should come close to them or not close to them, or what even matters in the problem, that's a reward assignment.
No, I understand credit blame assignment problem difference. I was asking what the difference is between credit blame assignment and this question of inverse reinforcement learning.
So credit blame assignment, that's reinforcement learning in general. Inverse reinforcement learning, we don't have these rewards. The reward function is not, so in Markov decision processes and reinforcement learning both, we're given the rewards, and the rewards are known to us, and we use those rewards to do the credit assignment to solve the problem. In inverse reinforcement learning, we assume we don't have the rewards, but we do have examples. So for example, I learned to like when I learned to drive, right? I don't really, some people don't actually know even the rules of driving. They just look at other people driving, and from that they infer what to do. For example, in Montreal, right? We can infer that people don't actually have to stop at stop signs. They only have to slow down. That reward function, that idea that when you get to a stop sign, it's not necessary to actually stop, that's not encoded anywhere. It's only extracted through observational data.
I'm going to ask that to be removed from the tape.
All right.
Because that's illegal.
Although it is a universal, I mean, it's true, like they have the rolling stop. In many places I've lived, including New York and California, people have told me, the rolling stop is a unique thing to our city. Well, okay. Anyhow, so I want to talk a little bit of coral reefs because it's an important domain where we work in, and I do want to just motivate it. It's very quick. I'll just mention that most of the world is, of course, under the water. Most of our planet is under the water, about 70% of it. It's super important, and it's tremendously overlooked in robotics in general. There are people working in marine robotics, but a very small minority. If we look at the health of coral reefs are super important in terms of many aspects of life on Earth, both the biosphere and also carbon sinking. In 1975, if we assumed that 100% of reefs were alive, like that's our baseline, around now, about half of those reefs from 1975 are currently dead. And in 2050, the prediction is that most of them will be dead. And by the way, between 2018 and now, we are tracking that sad trajectory quite well. So, this is an example of one particular reef where there's good longitudinal data. And we can see that between 1975, when this was a healthy ecosystem, and 2014, where it was a dead desert, the trajectory has not been very good. And so some of our work involves going to reefs and trying to make measurements on what's there in the hope that this will assist in understanding how to address these problems. Because most of the problems on reef are anthropogenic. They're caused by people. So for that work, we use a vehicle that looks like this. It's a six-legged hexapod. Hexapod, of course, just means six-legged. It can swim for about 6 hours. It can swim faster than I can, and it swims around underwater. It can also walk on land. And so I'll show you a little bit of work using this vehicle, and using this vehicle to do data collection under the guidance of a person. But in that notion of the interplay of behavior and interaction and perception, most of our papers deal with some perceptual problem, collecting observations, mapping the reef, taking vision. Let me mention that before you get there, you've actually got to control the behavior of the vehicle itself, the swimming. And so, how do we get gaits for swimming? So, if we think of human learning, I think humans start something like this, maybe a little bit more elegantly. And what we want to achieve is something kind of like that on the lower left. I'd like to claim that's me swimming, but that's actually Michael Phelps, the Olympic champion. And so the same kind of thing applies to our robot. We'd like to go from very primitive, simple behaviors to complicated, elegant behaviors, if I can abuse the word elegant a little bit. And I'll show you a very quick example of doing that using RL. So in this work, we use transfer learning as a component. So it's reinforcement learning, but we have two domains, a source domain on the left, a target domain on the right. The target domain is swimming in the real water. The source domain is simulation. And so what we'd like to be able to do is learn in simulation and then transfer those results to the target domain. Now, when we do that, the simulation is imperfect, and so the transfer is imperfect, and we still have to learn in the target. The idea is that using this kind of policy transfer, we can make things better. And so here's an example of this learning taking place. So this robot is trying to learn to swim to the end of the pool on the left and back. And in the upper left, we see just a second view of the problem. And so you're seeing now by the fifth iteration, it's actually getting there. So I should mention that this looks super fast. This is twice real time. And there's a tether connecting the robot to the cloud. And so it's doing some of the computation offline using larger computing resources that can be on the robot. And so I hope what you saw there is in 8 iterations, which is astonishingly fast in this kind of problem, we learned to swim across the length of the pool, how to control our robot to get appropriate gaits. So that kind of component behavior is just one little piece of all of the other problems we want to solve. So I want to think about the problem of learning by following a teacher. And it's the kind of thing that photographers do, right? It's a big game. And so here's an example of photographers that have to run around and take pictures. And the question is, you know, who do you follow? When do you follow them? How do you learn what they look like? How do you track them? It seems like a very simple problem. It's a ubiquitous problem. Taking pictures of people is a thing that people, you know, are very preoccupied with. And tracking them is really important. And sometimes tracking them is really complicated. There's a photographer chasing a guy in the car after he's committed a crime. So, and I think it's easy to overestimate how easy the problem is. Sometimes even for people, the problem is not as easy as it might look for many reasons, including kinematic control. Of course, that's really a robotics problem failure we just saw here. So I want to talk about vision-based following for robots and then learning from people who do guidance. So in the upper left, we're seeing a robot following a robot. On the right, upper right, we're seeing the Skydio companies flying robots who can follow you. They're super cool. And there's a number of other examples of that kind of thing. So let's just think about how to do that. So here's a simple example of using a deep net to do tracking and following. And this is the case that you saw in the upper left a minute ago, where one robot is following the other. And it's a relatively simple problem in the sense that we can collect video of the first robot and train a neural network that understands its pose, its, you know, which way it's facing and how far it is and how it's moving, and then follow it. The problem is, what do you do when that tracking fails, when it's interrupted by something? And that's always true. And so if we think of the kind of simplifying assumptions you can use for tracking, on the left-hand side, you can imagine problems where the subject is fully predictable. Excuse me. So we know what our subject is going to do, and we can extrapolate and move forward. On the right-hand side, we can imagine problems where the subject is adversarial. It's trying to hide from us, and we're playing hide and go seek. And that's a very interesting problem, but it's probably not the one I want to talk about today. In between, I think we have the most realistic problems where robots are trying to learn from people. So the subject's behavior can be inferred, and they probably want you to follow them, but you need to somehow be able to predict what they're going to do so that they don't have to be constantly connected to you. And so in that case, we're going to plan using partially observable Markov decision processes, basically reinforcement learning technologies. So our tracking approach involves detecting the subject. And when the subject is detected, we do reactive or model predictive control, the kind of thing you saw with that neural network, where we just predict what the next state is going to be just a very short time ahead and follow them. The harder case is when we can't detect them. We have to generate hypotheses for where they're going to be next and then visit those hypotheses to minimize the amount of time it'll take to find them. And so I'll show you a little video of doing that. Oh, I guess I won't show you the video right now. I'll talk about it first. I'll come back. I promise to show the video. So this is the case of the simple case, the following, right? We saw that very briefly. I won't spend time on this now, but we'll just note that in the lower right, that's the robot's internal model of what's happening, and it can see its target robot all the time. So learning for the back robot to learn from the front robot is quite easy. It's a valuable problem because in this particular instance, the front robot has much more expensive equipment. So it's much better at formulating plans of where to go. And the back one is trying to learn those notions of where to go and what to do by following its leader. The question is, when we lose a target, how do people navigate? How do we capture their behavior? And for that, we use inverse learning. We watch people and observe what they care about. So we're going to generate hypotheses, as I said, and then visit those hypotheses. So here's a simple example on land. In this case, we have a subject on the right. We have a follower robot, a blue triangle. It's got a limited field of view, that yellow triangle, roughly that yellow triangle. And we know a priori that the subject is likely to go to one of several locations. And we're going to presuppose we have some probability distribution over those locations, although we might assume they're uniform if we don't have enough notion of where things are going. And we'd like to generate likely trajectories for where the person is going to go, and then try to guess where they are on those trajectories whenever we can't see them. So these trajectories, we'll call them tau, they're labeled. They can go over cement or they can go over forest. And so the question is, are these trajectories more likely over the pathways, Or are these trajectories more likely, the ones that go over grass or whatever else those other materials are? How do we compute the trajectories, the guesses for where people are likely to go? And then how do we locate them on those trajectories? So in this case, we assume the subject has some internal notion of reward. Maybe they don't use exactly reinforcement learning, but they use some surrogate, some notion of what a good trajectory is. And we can compute a function that weights how desirable it is to walk over trees, how desirable it is to walk over a road, how desirable it is to walk through a building. And so at any time, we can learn the kind of trajectories that is best by observing humans and observing their behavior. And in fact, this can be personalized on an individual person basis. So some people might prioritize speed over comfort. Inverse reinforcement learning involves maximizing some complicated function where we take some expectation over all the trajectories and we try to find rewards that match our experiential data. And I'm not going to talk about that in detail, but the simplest thing is we can consider all the possible trajectories that could have been taken and then try to infer the rewards that would have explained the way the policy was generated such that the outcomes were the things we observed. So we can estimate the rewards that the subjects must have used in order to lead to the policies that they got. Of course, we have to have an underlying notion of actions and states that are somehow consistent with what humans are using. And so there's a kind of big leap of faith here that we have some basic model of how the humans are likely to behave in our world. And so in solving this problem, we do some offline planning, we compute a value function from those rewards, then we compute a stochastic policy, how we actually want to act, and then we can sample the trajectories and try to find the person. And then we're going to visit the hypotheses for where the person is to minimize the expected time to find them. So we'll see all this kind of rolling out in a video finally. One last piece I want to mention is when we lose track of the person, we'll infer that they're on one of the trajectories that we think must be the plausible trajectories based on this reward notion. But then we also have to develop hypotheses for where exactly the person might be on that trajectory based on where we last saw them. And we'll use a technique called particle filtering here. Basically, it's just having multiple hypotheses that all run using some internal model of motion themselves separately. So it's like having many hypothetical people walking the path every time you lose it. And you'll see these green dots moving along the path. And then once we make an observation of these particles, either we see the person there and confirm that they're where we thought they were, or we see they're not there, they're disconfirmed, those particles vanish, and the remaining particles must be the truth. So here's that thing finally running as a video. So initially, we've the follower, the target, we've just lost the person for a moment. And so we have lots of little green dots, hypotheses of where they might be. They're basically where we left them. We know the potential locations that they're going to, and we're going to assume that we can guess the probabilities. Although in this case, you see the probabilities are distributed almost uniformly. So now we're seeing the system run. So we're basically, every time we see the person, the particles go away. Every time we see a particle, the other particles go away, and we finally track them successfully. So here's another example. This is called topological pursuit, because we compute a topology over the environment of the trajectories, and then we use this particle filtering on top of that. And the trajectories are computed using this IRL technique. And so you'll see that, at some point we lose the person. They could be on multiple paths, but then we mow all the particles down on one of these incorrect paths, and then we can go and find them on the other path. And so this seems to be surprisingly successful. And surprisingly successful is my, my attempt to be modest. And in that case there, we saw the robot get ahead of the person. All the hypotheses were then behind, and it had to turn around and go back and find the person behind it. So this is an alternative method. This is, I guess, state of the art in 2018 that we were competing against. And I guess the notable thing is it does kind of less well in this scenario than our own method. You'll see that the particles are wandering around. The robot doesn't succeed in finding them very effectively. So I won't dwell on the results, except to say that in terms of the amount of time it takes to get contact and the amount of contact, this approach seems very effective. So it's an interesting way of following people. And then this notion of following people lets us then learn what they might learn. So now I'll look at deploying this on the aqua robot to collect data in the ocean. So that aqua swimming robot you saw before uses cameras, a depth sensor, an inertial measurement unit, an IMU. It has some other gear on it, including GPS, which requires it to surface and find out where it is. And all this gear lives inside the robot. So these three stacks, a control stack, a vision stack, an AI stack. AI stack basically runs convolutional neural nets. It's a GPU stack.
Can I ask a question?
Some things on the gear. So in terms of a metaphor, you can think of the control stack as being like motor cortex and cerebellum. It takes care of motion, and it in fact keeps the robot safe when the higher level planning processes fail or go wrong. You can think of that middle box as being like your hippocampus and frontal cortex. That's your planning and your memory, your notion of where you want to go. It's also, by the way, where experimental student code is typically deployed. So that's the part that could fail, and that's where the lower level pink box takes over. And then on the right, we have something that you might think looks more like visual cortex. That's the deep net that interprets our visual feedback. And then we have legs for motor control. So that's just an analogy, but nonetheless, it's kind of a nice way to think about it. It was not designed with that analogy as a target. Just kind of, after we developed this system, we realized, hey, there's a nice mapping. Here's an example of that, the versatility of this kind of design in this robot. So in this case, it's learning to swim and learning to walk into the water and do what we'll call surf entry, surf exit. This is a really hard problem. There's a lot of beautiful cases of why it's hard, but you can imagine sometimes the waves come and turn over the robot. And it's a case where we don't have any really good formal models of how to solve the problem. So we have to learn some of this by human control. So here the robot is being controlled by a person. I'm trying to learn from them how to solve the problem. Really, we're just showing off that the physical system is capable enough. And this is kind of ongoing work, but it kind of shows you what's capable. The problem that we've had more success at solving so far is, where should the robot go? What should it look at? Where should it collect data? And so we'd like to adjust the trajectory of the robot underwater to cover texture-rich regions and increase how well it can do odometry, and also collect data that might be of interest to people who are trying to study the reef. So that second part of studying the reef, I won't talk too much, but I'll talk about the navigational part first. So the idea is we can use the front camera to predict things that are good for odometry and navigate towards them, things that are high scoring in terms of this thing of being good for odometry. And then we use the back camera to actually do the odometry, to observe underneath what texture is passing under us, to build a notion of where we've been and what our trajectory is. And we do this using a complicated combination of neural networks, model-based reinforcement learning, and model-free reinforcement learning. I won't talk about the details, but I'll show you some of the kind of results. And there's a deep net in here to do the so-called perceptual part of learning these features on the ground and figuring out where to go. So in terms of navigation, we steer the robot towards areas that are going to be the best, and then we use smoothing over time to avoid problems that come from the perceptual system. I got a little too much of this based on our time flow. To do the labeling and choosing what's interesting stuff to swim over, we use human labeling. So humans have to look at these images and say, I want more of this, I want less of that. In this particular case, we don't want to look at fish, and we don't want to look at dead coral or sand, and we want to see live coral and healthy coral reefs, which is what we're trying to enumerate in some of these experiments. And we have to do some segmentation of the images, basically to train the image. So humans have to get in here and look at data collected from the system and label it, and provide us a notion of what it is we should be doing. And they also have to give the system feedback on how to do the collision avoidance. So if we're heading towards a reef, if this is the image we're seeing, on that image on the left, we don't want to go towards that coral structure. We want to move to the left and up. And on the one on the right, we want to move also to the left and up to get closer to the coral to get a better view of it. So we have to teach the system manually how to avoid obstacles, how to avoid sand, how to explore interesting things, all these prerequisites that allow it to navigate and collect data. And doing this in real time in the ocean is obviously essentially impossible. So for that, we use so-called sim to real. We run a simulation, we combine training in simulation with real data. You can't use this without real data, but you can augment real data by collecting way more data that has to match distributionally in terms of behavior and actions, but you get way more examples of what to do. And so with this kind of sim to real paradigm, we can generate hundreds of kilometers of swimming data, whereas in the real ocean, we can only generate kilometers worth because it's so time consuming and person consuming to collect that data. So here's an example of that kind of thing going. Here it is avoiding sand to stay over coral in the upper left. Here it is avoiding the sea floor and pitching up to avoid, say, a coral head that we don't want to crash into. Again, to collect the data and do the training, we need a human supervising it because before it's learned, there's some risk that it could damage the reef or maybe the robot. And in addition, we need to basically make sure that things are operating well. So you can see a diver occasionally behind the robot. Here's an example of the system working well. So it's basically, moving away from something you don't want to hit and still doing well. And it does about 93% accuracy. I'm going to skip the video. Here's an example of this same robot swimming after the person. So here, the target is to follow a person. The person is instructing the robot where to go. It has a camera looking at the front that follows the person. So it's teaching the robot what a good navigation strategy is in real time. It has a second camera that looks at its belly. And so every now and then you see it swim on its side like this. So what it's doing now is it's following the person with its forward camera and it's looking at the reef with its so-called belly camera. And every now and then it'll also flip the other way to look in the other direction to see if there's anything novel that it should be paying attention to. And so there's three components here. There's tracking the person and keeping them in sight. There's collecting data on the parts of the reef that are presumably interesting. And then there's looking for novelty in places that we have not looked before. And so we have to look at the things that the human found interesting and maybe keep an eye out for new places to look. If we let this video run further, there's also a component where the robot gets the person's attention by swimming over something interesting to tell them that they should come and look at something that might be noteworthy. So now let me take a little segue and talk about navigation in the presence of people in the environment. Oops, just checking my time. So what are appropriate controllers for socially appropriate navigation? I'm going to do this pretty quickly. So-called social navigation. How close do you come to people on land now when you're navigating around them? What is they moving? That's a pity that's not in English or in French. How are they moving? How should you be moving around them? Note that the behavior that we exhibit is context dependent. So if you're in a restaurant or a garage or a bus station, the social cues that you should be using are not always the same. And is it okay to do things like come closer to the back of a person than the front of a person? And can we use reinforcement learning methods to learn policies directly? Well, the answer is no, because we don't have those reward functions that I mentioned earlier. So again, we have an inverse reinforcement problem. We can observe people, but we have to guess what the cues are that people were using and how it works. So standard navigation controllers for this kind of problem, and they've been used extensively. Many people have built, cocktail party robots or service robots, things like that. They often don't yield to humans. They don't get out of your way. And if they do yield to humans, then they end up also yielding to dogs and water fountains and garbage cans and anything else, right? So they don't have a clear model of how to behave with respect to human beings specifically. They may collide with people if they move unexpectedly. And they need a notion of human motion. They may act in an impolite manner or an inappropriate manner. And I think a correlated issue is how you get people's attention when you move in their proximity in order to interact with them or request them to move. So in some contexts, I've seen examples of, say, cocktail party robots where the room is a bit crowded and the robot can't pass through the room. And so it has a very simple controller and it just backs away from people. And you may well at the end of the evening find the robot in the closet or in the washroom or somehow where it's ended up getting pushed away. And so what we've seen in airports, what you've all seen in airports is we have systems, machines that can beep or honk. That's generally not a socially appropriate action, especially if you imagine it in a restaurant or a home. We have a nice little paper that we did at Samsung a couple of years ago on how to attract people's attention in a socially acceptable way. And one of the nice results we found was that blowing a little bit of wind on the back of somebody's head is a way of identifying a single person getting their attention, and then they can look at your screen. And that's not what I'll talk about now, but it's kind of a fun little result. Understanding social navigation does involve taking a lot of human data. Personal space and the social conventions are really important. They're well recognized. They're very hard to encode algorithmically. There's a lot of work on encoding them algorithmically, but all of it is fragile in the sense of taking into account context and timing and environment and even what part of the world you're in. So many of these complicated rules have been formulated. One of them is common ground, but they don't, I argue, they don't really work generically and robustly. You can also use those kind of rules to predict the motion of other people's, and that's an ongoing problem. And notably, personal space and gaze direction can be encoded algorithmically as well. So you can encode where people are, where their face is, where they're looking, and take that into account. And that's proven to be quite beneficial. So if a robot is coming down the hall and you know that the person is looking down the hall, then you should move to the side and let them pass. So our approach involves using inverse reinforcement learning. As I've mentioned again, learn those implicit rewards explicitly to do this motion prediction. We observe human motion, in our case, using overhead cameras, observe the trajectories of people over time. We infer the rewards, and then from those inferred rewards, we can infer controllers and build them. Inverse reinforcement learning, I should note, is expensive in terms of the amount of data it needs, and also in terms of the computation. And so we've spent a lot of work doing sample efficient inverse reinforcement learning, basically learning methods that can be trained with less data. And that's a technical sub area, but it's a kind of an important one. And so I won't show you demos. In fact, a lot of this work was being done during COVID, so a lot of it is done in simulation. But we introduced a notion of risk, what parts of the world are the highest risk and the lowest risk, what's bad. So we had to formulate a representation of the world, which is typical in this kind of problem. And then over that representation of the world, for example, the robot is in the middle of a circle, the circle is divided into segments, people can be assigned to those segments. Then once we have that representation, then we can do inverse reinforcement learning and learn how those representations of the world, those states, transform into rewards. But notably, the state representation itself in this problem is actually not a well-defined thing. We use risk-based features that exemplify or capture the notion of how dangerous it is to come close to that person in terms of collision. And we use LiDAR, so laser-based sensing instead of just computer vision. And we achieve smoother and less intrusive trajectories than some similar methods. And so basically the movies of this look kind of like these tracks on the bottom. I won't play the movies because I think I'm tight for time, but I hope you understand the notion. Basically, we come less close to people, we don't collide with them as much. So I think I should wrap up there. I think this is my time budget. Is that right, Stephen? Well, I'll wrap up there.
Can you hear me?
We'll see. We can chat more.
Can you hear
So
me?
intelligent behavior, intelligent robotics, all depend on using and understanding human guidance, I think. That's really where we're at. The last 20, 30 years of robotics has been building the core substructures that let us play toys in the lab, play games with toys in the lab, and maybe some very simple experiments in the real world, but not roll out robots in general because human interaction needs to be taken into account. And I'll tell you, as a roboticist, taking into account human interaction and human behavior is horribly painful because people are unpredictable, they're hard to model, and you have to do experiments with them. And those experiments take a lot of time and energy. So that's the game that I'm playing now. I love it, but I also hate it. When I don't work with people, I say, man, I hate robots. And when I work with people, I think I love robots. Human-robot interaction and related areas, computer-human interaction, have a very long tradition, but I think they tend to be a little bit overlooked by the core robotics community, the algorithmic robotics community. And I think that's something that is changing and needs to change. In our national robotics network, the NSERC Canadian Robotics Network is one of the priority themes to focus on human-robot interaction. And those models of human interaction can be both implicit and explicit. So, explicit teaching, having a person explicitly teach the robot, show it where to go, give it examples, but also observe people and figure out what their underlying motivations are. I think that implicit side is super important because the explicit side means you have to have people who are very dedicated, and that's really, it doesn't scale very well to the real world. If we want to learn how to drive and what all the social cues are, we can't have every driver in the world teaching our robot how they expect it to behave. So many of the methods that have been developed worked, but humans need to be in the loop for most of the meaningful problems, I think, over the next decade. And I think now that the field's matured, they can finally take this into account. You can't take into account human interaction until you have robots that work robustly, and we're finally kind of there. I think in the intelligence, in the absence of these social factors, these social interactions, is almost an oxymoron in the sense that intelligence is almost ubiquitously a phenomenon that takes into account the interaction of other living agents in the world. And so, as I mentioned, even fruit flies take societal cues into account. And I think I'll pause there. I have a few more slides, but maybe that's, and I think that's my time budget.
And I want to thank you very much, Professor DUDEK, for your presentation. Thanks, Professor Meunier, for your intervention. And with that, I think we can end the session.